And we'll get this going over here. Scala or Spark, collect, and plus validation. Thanks too. Okay. Ladies and gentlemen, the last time we saw some beginning use of Spark pipelines, and I want to, and we saw use of ML. I'll just very briefly recall this, but basically we loaded in some data. We labeled the data using ground truth indicators that indicate how each line of the data should be classified for the purposes of training and evaluation. We were using data from tweets, and we used a case class to convert from data frames to data sets. You may remember that allowed us to work in a type-safe way. We initially had two disjoint sets of data that we ran in. We read, but we ended up combining them, taking the union of them. So all of that was in a single data set. That is both negative and positive examples. Both types of cases were combined. We then split that full set of data, which included both samples of cases, into two sets. And we use this to sort of, I motivated that by a bit of reference to cross-validation. We then composed, in a series of steps, a pipeline, which consisted of several elements. Each pipeline element took data from the previous pipeline element and mapped it to output, which could be used by the next one. These elements were suitable for applying to Twitter data, to text data. They involve manipulations of text and then some analysis associated with it. So we had a word splitter that divided up text from a tweet into words, to individual tokens. We removed tokens that were judged to be not terribly significant. And both of these, I argued, were transformers. They weren't estimators, they were transformers. So Spark Scala, as I covered last time, delineates two types of things. One is transformers and one is estimators, okay? So transformers, when you specify it, you can directly transform some data, put in a data frame and get out a data frame, or put in a data set, get out a data set. We made use of that using this. So we did a transform here. For example, we transformed some data and we got out from the word splitter, and we got out data that was split up into separate words. Alternatively, with the trivial word remover, this was a transformer as well. We could transform the input from this last operation, and we could output the significant words from it. So it ended up removing certain types of words that were very common. So, you know, Ben feeling so sick turned into feeling sick. Okay. So that was transformers. Okay. That was transformers. Estimators, by contrast, were things that needed, so before they could be applied to a data set to perform their action, they needed some other data. They needed to be estimated from some underlying data, okay? And we made use of a estimator from a presence or presence or absence vector. So here we want to map words. We want to take some text, and ultimately we want to indicate which words are in that text. We want to indicate, okay, this word is in the text, that word is in the text, that word is in the text, these words are not in the text, etc. But But we can't just apply this directly once we create it. It's not like a word splitter, which is a transformer. We could just, once we create it, we can just apply it to some data, get out data. It's not like a trivial word remover where we can take in some data, apply it, and get out some data. Rather, for this word vectorizer, before it can do its job in indicating which words are present, we need to tell it about what the vocabulary is, which words it's looking for, which words it's trying to judge are present or not. So if we apply it to a single tweet, it will tell us, okay, of these thousands of possible words that we're interested in, which of them are present in that particular tweet. Okay, so an estimator's job in life is to first take in a set of data which allows it to be estimated, to be sort of calibrated for the appropriate situation, and that returns a transformer that can then be applied to data and get to data and put out data, return data. So, ladies and gentlemen, we had this with this count vectorizer, and before we could apply it with a transform, we fit it, as we say, we fit it to this data, and that gives us back a transformer. Okay, so we get out of that count vectorizer model that is a transformer. It's all calibrated. It's been fit to this data. It knows what words to look for. And having done that, we have this vectorized model we can then call transform on it because it's a transformer. We started, the estimator here was this thing right here, this count vectorizer. But by fitting it, we got out a vectorizer model, which is a transformer. We could apply it to data and it gets back data. You see that? Okay. Okay. So continue. Yes. Oh my gosh. Thank you. Thank you. Much appreciated. Fortunately, I've been having the dual presentation. Okay. Great. Thank you, Lucia. Is it showing now?
Yes.
Okay. 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 So with that in mind, with these kind of vectorizers and transformers, so estimators and transformers, we then work to create a logistic regression in the final minutes of class. So here we specified a logistic regression, which is, what do you think that is? Is that an estimator or a transformer? Like, can I just say, I have a logistic regression, apply it to this data? No, I have to fit it first. I have to fit it in a way that its coefficients will be estimated. It has a bunch of coefficients, beta coefficients, that say basically, you know, how much does the presence of this word or that word tell you about it being a health-related tweet or not? And as such, it can't just be applied directly to data, the logistic regression. It has to be turned into a specific model, and that model can then be applied to data. But the other thing that we needed to grapple with was the fact that before this could be applied, before the model could be applied even, we needed to do some data pre-processing. So if we tried to apply it to a bunch of raw data, it would not be very effective. It needs data that is tokenized. It needs data that's turned into an indication of whether it has or does not have a word, that trivial words have been removed, where words have been split up. Before it can do its job, it needs all of this pre-processing done. Do you see that? So in order to capture that fact, we defined a pipeline. Now, this pipeline knows how to perform all the pre-processing steps and then perform a logistic regression. But the pipeline, because this last component of it here is an estimator, like most pipelines, it's an estimator. And as a result, before we can apply it to something, we have to fit it. And that gives us a model, a fit model that knows how to do all the preceding steps. It knows how to process things and so on, okay? Now, having obtained a model, having fit it to certain data, we could then, it's a fitted model that knows how to get all the data into the form it needs to do its job. And we could then transform other data with it, okay? So this was the idea that we explored last time. And it turns out that these transformers that come out of this, or these pipelines, are very useful for performing data sort of processing needed both to train them, on the one hand, to fit them. It encapsulates all that work needed to before it can be fit, the underlying model. So, where you have to split words or remove trivial words and convert them to something which maps them to presence or absence, all that has to be done when we're going to fit. But it turns out all that has to be done as well when we're going to transform data with the result. Okay, if we give it a bunch of raw data, it has to go through those same steps to take that data in a form that it can then output data. It has to go through those same steps. And in fact, if we're going to evaluate it, if we're going to evaluate the model that's in this pipeline, it also has to go through those steps, because we're going to be giving it subsets of data that weren't used to create it, to fit it, and then using and seeing what it predicts for them and comparing it to the ground truth. So in short, the fact that we define these different steps in a pipeline, and we reify a pipeline, we represent it as a specific object. The fact that we're doing that is a reflection of the fact that it's pervasive. We need to go through these processing steps, not just for training, but for training and for testing, for evaluation of it. Not just for training and testing. For applying the final model, we're going to have to go through these same basic steps. So we reify it. We capture it in an object, this pipeline. And we then fit that object to get out a sort of fully, it's a fully qualified pipeline. It's one that can fully do its job. It's fit, and therefore it can be used to transform data. And all of these steps are being used for that. If we didn't define a pipeline, we'd have to apply each of these steps for each of the types of data that we're using to train, to fit, or to test, and to apply it. But here, they're all captured in the pipeline. So pipelines are very important higher level concepts. Using the pipeline, we were able to then have an evaluator which was going to evaluate the quality of the results, okay? And specifically, this evaluator, we told it sort of, okay, how to judge the results. Like, what's the ground truth label? This is the ground truth label. And what is the prediction of the pipeline? Where does that live? And how do we want to judge it? This is area under the ROC curve, which is basically judging the sensitivity and specificity over many, many different variants of parameters. So sensitivity and specificity trade off with each other, as you may know from a machine learning class. We can be super sensitive, detect every single one of the things where it's a true positive, just by trivially just always saying it's positive. It'll be allow us to detect every one, but its specificity will be very poor. We'll be saying all these things are true positive, which are not. All these things are positive, which are not really. Conversely, we could be super specific. Whenever we say something is, well, it definitely is, by just never saying it is and just always saying it's not. It's not the case. And everyone that that we are saying is the case, which is none, will be very precise. So we can trade off sensitivity and specificity. And an area on the ROC curve allows us to specify not just for one sensitivity or specificity pair, but over a wide range of pairs, sort of how well does it do? It's a key thing for judging classifiers that goes beyond any one setting. So this evaluator, we can then use that evaluator according to the area under ROC to evaluate this logistic regression from pipeline, okay? Logistic regression from pipeline being here, the results of this fitting. So it'll say basically, how well did it do? And, well, it did pretty well. But we don't know. We don't know why it did so well at this point. We still don't know, like, which words were really helpful for it. Which things were really helpful in allowing it to classify, okay? So we further did some things with different subsets of the data. So we had divided the data into subsets, and we fit it to a first subset, and we transformed a second subset, and we could then evaluate it as it's trained, as it's applied to that second subset. You know, up above, we kind of cheated in a way, right? Up here, we trained it on the same set of data we evaluated it on. We kind of gave it the answers to the test beforehand, right? I mean, I'm exaggerating a bit, but it's kind of like that. When we were training it, it knew about the same examples we're going to use to test it. So it's not terribly surprising that it was great. It was just super great. But here, if we fit it to a different subset of the data, and to one subset of the data, we transform it, we apply it to another, and use that application where we're trying to predict, to judge it, to evaluate it, we find it's actually much less efficacious. It's like an area under the curve of 0.71, which is not great, because an area under the curve of 50, of 0.5, 50% would be like guessing if we had equal numbers of both cases. So it's not that great, 0.71. Better than guessing, but still not great. And then we could do it the reverse direction. We could, you know, fit it to label 2 and then apply it to label 1. Okay. Now I realized these are actually my notes for last time. The actual one we did was only slightly different, and I'll go to that just for familiarity, because we're going to extend it here. Where is it? Where are we? Here we no. Where is my March 27th in-class session? Can you help me? Anyone help me find it? Yeah, there it is. There we are. Boom. Okay. Come on. Here we go. Okay. So this is what I had basically planned to do, and now we are going to continue on this example. Okay. Now I did some things after this that are going to anticipate something that we're going to do today. So I'm going to get rid of that. Okay, there we go. Great. Okay, so ladies and gentlemen, let us now press on. Okay. Any questions about that thing we did last time? Any questions? Okay. Do you still have your things fired up? If you don't, you can re-execute them, but it will be helpful if we still have these around. So, you know, in my case, we still have these various things, and so I'm going to continue with them. Okay, it'll allow us to make progress quickly now. So we got some decent results out here. We evaluated the results of fitting, and we got a pretty healthy, I mean, it's okay classification. It's about 0.5, okay? And we did that with different subsets. Great. So What we're going to do, though, is look into why did we get those results, okay? So I'm going to take this here, this logistic regression model that came out of the fitting here. So up here, we had done a fit. Well, excuse me. We are going to, right. So we're going to take this one that came from the Fed. It's just above here. This logistic regression pipeline model. This was the thing which we could transform. Remember that to classify things. This logistic regression pipeline model. We're going to take that, and we are going to look into its characteristics. Like when we fit it, what came out of that? When we did this fit, how did it think it was? What did it think was important in classifying a health-related tweet from a non-health related tweet? Okay. So after all, the fitted model has that, regardless of how many times we subsequently applied it. The fitted model, the fitted logistic regression model, has to have beta coefficients by which it thinks certain things are important and certain things are not, right? Similarly, a decision tree model would presumably be dividing cases according to certain attributes. So we're going to take this, and I want to ask some characteristics of this. First of all, I want to see how many stages are in it, in this model. And the answer is it's 4 stages. Any idea where those 4 stages came from? In that fitted model, where did those come from? What did those reflect? Yeah, exactly. They reflect these, ladies and gentlemen. What was in the pipeline? The word splitter, the trivial word remover, map words to presence vector, and logistic regression. There's 4 elements of that pipeline, and in the fitted model, there's 4 elements that it retained, sort of in this model. So we're going to now explore some components of this. Okay, so specifically, I'm going to do the following. I'm going to take this pipeline model, and I'm going to extract the 3rd component, the 4th element of it, okay, where this is element 0, 1, 2, 3. So it's the last element of it, right? Because we're 0 indexed here. So I'm going to do here best, here we go, val best LR model equals this guy here. And we're going to say dot stages of 3. Okay. And we're going to say as instance of, and we're going to say logistic regression model. Yeah, I know you can't see it that easily. Here we are. Okay. So we've just extracted from this pipeline model the logistic regression model that that was estimated. Okay. Now, there's other types of information in here we'll sometimes use. For example, there's a thing called a param map, which is sometimes of interest. See this? So see in the 3rd stage here, there's a extract param map. We can actually get that through this best LR model that we defined. So here, this is an instance of that, and I could say, probably it would have been clearer if I just said best LR model dot extract param map. Here we are. And you'll notice that what it's telling me is a bunch of characteristics of this model that we used. So, for example, we had a tolerance of 0.001. the regulatory parameter, the parameter associated with regularity was 0.1. It did 100,000 iterations. Where did those come from? At least some of them. Well, when we specified, remember up here? I don't know if you'd remember, but we set the tolerance, we set the regularization parameter, set this. This basically set these parameters that we see. So this will sort of provides metadata about what was matched, sort of the parameters used to match it. And often that's of interest. But let's take this LR model and let's go get the coefficients. Here are the coefficients for it, ladies and gentlemen. Now this is a long vector. Do you see that? Watch this. I could, for example, ask what's its length? What's its length? Dot size, sorry, not length. Size. 115. 115, ladies and gentlemen. I'd like to further say here, so we're going to actually name something for this, okay? We'll name these coefficients. We're going to be manipulating the val coefs equals this dot coefficients. There we are. And I'm going to ask how many of them are active and are sort of I thought it was non-actives. Sorry. Yeah, this is another way to get at that information. How many of these coefficients are actually present and recorded here? We could, moreover, say coefs.argmax and get the single, argmax, get the single largest coefficient. So that's going to tell us which of these coefficients are the largest. Now, what do you think these coefficients represent, particularly for some people here who have had more experience with logistic regression? What are the coefficients that come out of the logistic regression? Anyone remember? So that's the betas. Yeah. So each beta, with the exception of the first, there's kind of an offset beta term that's constant. And then the others basically specify how associated is that particular covariate, particular sort of thing you're using to judge. In this case, is this health related or not? How associated is that with it being health related? Okay. So if it's very positive, that's going to indicate it's highly associated. When you have something that's health related, this word is almost always going to appear, or it often appears. An example of a word like that might be, sick, or doctor, or hospital. If hospital appears or doctor appears, chances are this tweet is health related. Okay, so it's covariates, it's associated with it a lot, and these coefficients describe for different words which of them are highly associated with this outcome, association of health. Okay, so suppose we're interested in knowing which words these are. Like these ones that are highly associated, these 115 that I thought were significant enough to include. Which words are there? Notice, what would it mean if it's negative here? What if it's negative? Highly negative. What would that mean? It's pretty strong indication that it's unpredictive. Meaning, if you have that word in there, probably the tweet is not health related. So, maybe it would be Rough Riders or, or auto body or I don't know. I'm just trying to think of examples that that are unlikely to be health related. You know, sub freezing or something like that. Some word that's that often is associated with very different contexts. So now let's look at which words are associated with those vectors. Okay, with those significant coefficients. So I'm going to say val word to vector mapper model. So what we're going to look at here is we're going to look at this information that tells us which words are associated with this kind of these different positions in it. Does anyone remember which thing above was used to sort of determine which words are mapped to which components of a vector? Of all these things here, these four, whose job in life was it to say which words are associated with which position in a vector? Yeah, it's this guy here, the map words. But it wasn't by itself. Before that could be used, that had to be fitted. It had to be fitted to some data. And what data was it fitted? Well, it was fitted as part of the outputs from this guy, which were based on the outputs from this guy. Map words to vector basically needed to be fit to particular data in training so that it knew what words to look for. Okay, so we're going to be extracting this. Sorry, it's map word to vector model. We're going to look at logistic regression model. Okay, sorry, it's the thing we had above. It was this same one we used above with stage 3, this guy here, logistic regression pipeline model. But here, we're going to be looking at what stage of it? 2. It's the preceding stage. It's the vectorizer component of it. And we're going to say, get that as an instance of count vectorizer model. Oh. Okay. And now we're going to be able to work with that, okay? So if we do, for example, this, and we ask for its vocabulary, we could look at which of them was used for the very first here, okay? RT. Anyone know what that means? Retweet. Here's number 1, sick. Number 2 word, voted. Number 3, millions. Okay. So these are the various words in its vocabulary. Okay. Now, each of these words corresponds to a particular element in this vector of coefficients, because each word is associated with more predictive or less predictive components, okay? If you look at the ones we were just exploring, I should have included all of them. You know, word 0 was retweet. Retweets were not highly predictive here of a health-related thing. Word 1, by contrast, was quite predictive of a health-related thing. It has a about 0.27, this guy right here. And not surprisingly, that word, it was what? Sick. Yeah, okay. So, and then word 2, meanwhile, voted. It's not all that predictive, nor was millions, thank goodness. Okay, so we're going to be able to look at the vocabulary and find which vocabulary items are associated with the highly predictive ones, the ones that are highly predictive of the classification, okay, in terms of positive outcome, in terms of saying, okay, this is a case of sick. So I'd like you to do coefs dot to array. That's going to convert them all 115 to an array. Dot zip with index. Dot collect. Here's our collect. And we're going to do case v comma I if v is greater than 100. Okay? If v is greater than 100, then we will take this word to vector model. We will use it to look up in its vocabulary under which item. Anyone tell me? Which thing haven't we used yet? I. That's the index. Okay? Maybe I'll just explain what the zip with index means, okay? Can I just show you quickly? Watch this. Vector foo bar as zip with index. Guess what this is going to return? It's going to be foo 0 bar 1 baz 2, right? So these coefs, if we look at the coefs that, well, we saw them above, right? These coefs here. Each of them is going to be zipped up, as it were, into a vector of pairs. The first element of the pair is going to be what? Let me get rid of this extra thing. The first element of the pair is going to be the coef value. The second element of the pair is going to be the index, 0, 1, 2. And if we're dealing, oh, sorry, folks, there should be a this around there. And we don't need the open paren here. There. So what is this thing? What is this thing here? It's a what? Begins with a P. Yeah, it's a partial function. And it only collects those things. Remember we used collect before? It only collects those things for which the partial function is what? Defined. So it's only going to be those things. Oh, I said greater than 100, but sorry. Yeah, none are greater than 100. Let's do greater than 0.25. Let's say that. Okay. Oh, okay. So mumble. Collect. Okay. So what am I? Did I not have a? Yeah. There we are. Okay. Sick, love, illness, need. You young people, what is that? That looks like a emoticon of someone who's sick, doesn't it? Did they have like a mask over their face? Doesn't it? Okay, now I don't know about these others. You're one lost study. Okay, don't get any ideas. Studying doesn't make you sick. Okay. Maybe we can. Hey, well, let's go see what the biggest coef is, right? Coefs dot max. Let's go see what. Mumble. Sorry. So here we can do coefs. Can we do coefs of coefs dot argmax? I'm surprised actually it's not. Yeah, 1.69. Okay, so let's up our game a little bit. Let's look at 0.5, right? Illness. Okay, sick disappeared as a big explanatory variable. Why is that? Yeah, it's used in other contexts. People say, you know, this makes me sick to my stomach. And in fact, at this time, this was right after the US elections, and people were using sec in many political contexts. Okay, so let's go look at things that are highly non-predictive of sickness, right? What things are non-predictive of sickness? Not all of these will be appropriate, I might warn you. So let's look at things that are, so let's do argmin now, right? Let's go see an argmin. What's the minimum one? Are there some things that are terribly non-productive? Oh, there's no argmin. Well, we could map each to its inverse, to minus it, minus its current value, and then do argmax of that. Oh, map is not a member. What? Map is not a member of. Oh, it's a special vector. Mumble. Okay. There's probably a similar thing, but we'll just try minus 0.5. Okay. So let's try minus 1. So some things go without saying. Man is okay. It looks like man is not very predictive of health-related tweets, and like is not either. Makes Poxa. I don't know what Poxa means, but you also is not. Okay, so here we've sort of explored into this. I'd like to finish up here with just a few more elements. I'm going to define, so this is how we can sort of elicit which tweets are the results of the model and make sense of them in light of those words. Now I'd like to show how we could perform, time is short. I'd like to go into this in a little bit more detail. What we're going to do, I guess we'll just do it next time, is we're going to show how automatic cross-validation can be performed. And more than that, how we're going to be able to define a broad set of parameters that will allow us to question these parameters up here that we saw. These parameters that are associated with the best model. Here we have to commit to a max iteration. We have to commit to a particular value of the regularization parameter, particular value for tolerance. Where did we commit to that? Well, we had set that up here when we first defined the logistic regression. We're going to see next time how we can actually say, hey, look, try it for a bunch of different parameter values. Try it for different values of this, different values of that. And for each one, conduct a cross-validation, which will evaluate how well the model, the logistic regression using those parameters performs, and then prefer the model which has the parameters which offers the best cross-validation performance. Okay, that code is, if anyone wants to get a leg up on that, wants to try that before next time, you can actually go to the Moodle site for the class and download. I think it's this guy here, that JSON file, or this guy, and you'll actually see sort of code to do that, where I actually build that up. We're down to like this place here, but here you can actually see how you define a cross-validator, and then how you undertake cross-validation with it using a fit, and extract some aspects of it, including and use it to extract the best model, and then save the model away in a file here. Okay. So that's what we're going to be doing. Next time, we're going to go through that, and we're going to see how this cross-validation pipeline, again, eases that, but how we can, more than that, allow us to use this param grid to evaluate different possible parameter values. Okay. And that will allow us to avoid committing in to just one set of parameters as we did here. Instead of having to do it by hand to examine different sets, we could just say, hey, go examine this whole set of full set of different parameter values, different combinations. That is for next time. Okay. Thank you very much. And we will see you next time.